3.6, chew on this to solidify understanding task. Okay, so we're still dealing with our different kinds of sequences, right? Our patterns. So let's take a look at these first two questions. Mr. and Mrs. Gloop want their son Augustus to do his homework every day. Augustus loves to eat candy, so his parents have decided to motivate him to do his homework by giving him candies for each day that the homework is complete. Mr. Gloop says that on the first day that Augustus turns in his homework, he will give him 10 candies. On the second day, he promises to give him 20 candies. On the third day, we'll give him 30 candies, and so on. So it says, write both a recursive and an explicit formula that show the number of candies that Augustus earns on any given day with his father's plan. Use a formula to find how many candies Augustus will have on day 30 in this plan. So, pretty straightforward, right? My suggestion, as usual, let's start with a table. So we've got days and candies. So it says on the first day, he'll give him 10 candies. Second day, 20. 30 day, 30. And so on. So the fourth day would be 40. Fifth day would be 50. Okay? And then we want formulas, so we're looking for the x day. What would the x day be, right? Or the n. Okay, well, to do that, we need to think back to the 0 day. What would the 0 day been? Well, he wouldn't have got any candies that day, right? So, now let's make our recursive formula. Okay, so remember with recursive, we always start out by saying to get the next term, it's equal to the previous term, right? This stands for the input, and the f of x with the whole parentheses, or the f of x minus 1, stand for the outputs, because recursive connects these outputs. So what are we doing every day? We are adding 10. So we add 10. Now that's half of it. We need the other half. Where did we start? Well, when the input was 0, we started at 0. So there's our recursive. Now for the explicit, okay, that one's the one, well, we're adding, so what kind of sequence would this be? It'd be arithmetic. So that means we're using the slope-intercept form, y equals mx plus b. So we're saying, okay, we'll use f of x though, equals, to get the term, it equals, well, how are we connecting these? Well, we start off by going to the starting point, 0. And what are we doing to 0? We're adding 10 each time. How many times are we going to add 10 till we get down to x? X amount of times, so it's 10 times x. So we can just simplify that to f of x equals 10x. Which makes sense, right? If you're thinking through it. Because if 2 days, 2 times 10 is 20. 3 days, 3 times 10 is 30. 4 days, 4 times 10 is 40. So what would it be on day 30? Well, we'd go to 30 days. So you'd go f of 30. And then we evaluate the function at 30. Well, 10 times 30 would be 300. So at the point where the x value equals 30, the days equal 30s, the output, the y value, equals 300. That's the point. Okay? We could have also found it with the recursive equation, right? Thing is, we would have had to figure out what happened at 29 days. So basically, we would have had to just continue this table until we got up to 30, which we could do. It's a viable way. Takes longer, but it is definitely a way that we could still figure it out. Okay, so we still could have went, because that would be 60, 70, 80, 90, 100, and you'd probably see this pattern, 110, 120, 130, 140, 150, 160, 170, 180, 190, 110. So we're basically applying this recursive formula when we make a table, aren't we? Oh, that should be 200. Why did I go 110? Oh, because 190, so I was thinking 110. 200, 210, 220, 230, 240, 250, 260, 270, 280, 290, and 300. So yeah, you can use either equation to get it, but when it's so far away, it's much easier to use that explicit. That's why we like the explicit formula so much better than the recursive. But it still is helpful to understand how to write the recursive, because that basically is just, how we're making the table. Alright, let's jump to the next one. So Augustus looks in the mirror and decides that he is gaining weight. He's afraid that all the candy will just make it worse, so he tells his parents that it would be okay if they just gave him 1 candy on the first day, 2 on the second day, continuing to double the amount each day as he completes his homework. Mr. and Mrs. Gloop like Augustus's plan and agree to it. So, model the amount of candy that Augustus would get each day he reaches his goals with the new plan. Use your model to predict the number of candies that Augustus would earn on the 30th day with this plan. Write both a recursive and an explicit formula that shows the number of candies that Augustus earns on any given day with this plan. So let's start it off the same way we did the other one. So, make a table. We've got days. We've got candy. So it says on the first day he had 1, the second day had 2, the third day he didn't have 3 because they said we're doubling, right? What does doubling mean in math? It means we're multiplying by 2. So it means we've got a geometric pattern here, don't we? Which just is good to know. So that would be 4. Then on day 4 we would have 8. Day 5, 16, and so on, to day X. That's what we want to figure out, right? So to do that, we want to go back to day 0. Well, what's half of 1? It'd be 1/2, because 1/2 times 2 would give us 1. Okay, so now, it says predict, use your model to predict the number of candies. So once again, we could make a table and just keep going until we got to 30. Okay, but it's gonna take some time, right? But we could do it. Okay, you could do it that way. And if you had a calculator, there's an easy way that you can just keep going and count. You don't necessarily have to write them all down. But I'm gonna hold off on this one until we take a look at 5. Let's write our equations, our formulas, and from there it'll be a lot easier to figure out our answer. So remember, the recursive one is just like the table. So we say to get that next term, we take the previous term, and what are we doing? We're doubling it. Okay, there's half of it. Now where did we start? Well, f of 0, we started at 1/2. So remember, that piece is always the same on recursive, regardless of whether it's arithmetic or geometric. Okay, which, yes, we could use this to get our answer, but the problem with that is we're just basically making our table. Okay, so the explicit, that's the one we like. That's the one that makes it easy to figure out the bigger numbers. So with the explicit, we treat it kind of the same way we did this slope-intercept one. Okay, it's kind of the same way, except the difference is instead of adding, we're multiplying. So the way we write the formula is a times b to the x, where a is the start number, also known as the y-intercept, and b is the growth. We don't call it slope, but it's what we're multiplying by. So I go, and we'll use f of x instead of y again, because we used it up here. So f of x equals, we started at 1/2. What did we do to 1/2? Well, we times it by 2. How many times did we multiply by 2? X amount of times. And so we make it an exponent. So remember that when you're dealing with the arithmetic, okay, you're adding over and over and over, like 2 plus 2 plus 2 plus 2. And the shortcut for repeated addition is multiplication. That'd be 2 times 4, right? Because we have 4 2's, so when we have x amount of 2's, it's 2 times x. Whereas with geometric, we're going 2 times 2 times 2 times 2, so it's that repeated multiplication, which the shortcut is to the power, 2 to the 4th. Or if we have an x amount of 2's, it's 2 to the x. Okay, so now all we have to do is to answer number 4, so that was the answer to number 5, those two formulas. So to answer number 4, we just find that 30th day. So I go f of 30, because we want the 30th day for the input, equals 1/2 times 2 to the 30th. Okay, well what is 2 to the 30th? Well, that's 2 times 2 times 2, 30 times. See, and that's basically what we'd end up having to do to make our table. We'd have to do it that many times. So it's easy to just use a calculator to figure that out. So we get 1/2 times, and you can see why this explicit equation is much easier to deal with. Because 2 to the 30th is 1,073,741,824. So you times that by 1/2, or divide by 2, that's the same thing, and we get this number. So we get 536,870,912 pieces. So you can see there's quite a big difference between this geometric pattern and this arithmetic pattern. Okay, 300 as opposed to 536 million candies. So it's pretty easy to see which of these grows quicker, right? That geometric. Because you're multiplying, not adding. And multiplying always is quicker than adding. Alright, let's take a look at this last one. Augustus is generally selfish and somewhat unpopular at school. He decides that he could improve his image by sharing his candy with everyone at school. When he has a pile of 100,000 candies, he generously plans to give away 60% of the candies that are in the pile each day. Although Augustus may be earning more candies for doing his homework, he is only giving away candies from the pile that started with 100,000. He's not that generous. So, how would we model the amount of candy that would be left in the pile each day? How many pieces of candy would be left on day 8? And when would the candy be gone? Okay, so can we start with a table here? It's always a good place to start. So he gives away, so days again, and candy. Now there's two ways that we can think through this one. You can think about the candy left over, okay, which we're wondering when the candy will be gone, so that's probably the best way to go with it. How many will be left on day 8? Okay, how many are left in the pile each day? So they're kind of saying, do it this way. The other way would be, how many candy did he give away? Which are two fundamentally different questions. Okay, ours is talking about candy being left. You could have a situation where it wants to know how much candy was given away each day. Okay, which two different kinds of problems here. So let's take a look at ours. So on day 0, he started out with 100,000, right? Then on day 1, 2, 3, 4. So on day 1, he gave 60% of that away. Well, what's 60% of 100,000? Well, to figure that out, you would go 100,000 times 0.60, right? Because when you deal with percents, you have to make them a decimal. And you'd end up with 60,000. That's how many he gave away. We want to know how many are left. So the better way to think through this is to say, okay, 100,000 is like 100%. If we're subtracting 60% of that each day, how much percent is left? Oh, well, 40% is left. Okay, so really what we're doing here is we're going to multiply by 40%, because that's what's left over. Okay, the way to kind of think about it is 1 minus that 0.6. That's like 100% minus 0.6. You could multiply by that, but we know that's just 40% or 0.4. So that's the one we want to deal with. So whenever you're dealing with percents, you've got to pay attention to really what percent are we dealing with. Since we're taking away 60%, but we want to know what's left, we really think in terms of we're actually multiplying by 0.40. Okay, so if we take 100,000 and times by 0.4, that gives us 40,000 on day 1 that are left, because he gave 60% of that away. Then we're going to multiply by that 0.40 again, and that's what we're going to keep doing. We're multiplying by 0.4. So once again, geometric. And when you're dealing with percents, it's always going to be geometric. So we get 16,000 times that by 0.4. We get 64,000, actually 6,400 times by 0.4. We get 2,560. Okay, so we need to get to day 8, right? Now, could we make an equation out of this? Yeah, we could make a recursive, which is not very helpful, right? And it would look like this, times 0.4, and then it would be f of 0 equals 100,000. Not too helpful, though it does help us fairly easily get to number 8, right? 1024, 409.6, 163.84, 65.536. So yeah, 65 and a half candies, basically, a little more than a half, left on day 8. So that would be the answer for day 8, right? So when will the candy be gone? Okay. Now, if we wanted to on that day 8, we could have also found that explicit equation. We used the recursive basically making that table, and we figured it out. It wasn't too hard. For the explicit, right, we'd go f of x equals, well, we started at 100,000, and then what did we do? We times by 0.4 over and over and over. So our equation would look something like that, which we could have plugged 8 in and we would have got the same thing. Okay. Now, let's keep going with this. So 8, 9, 10, 11, 12, 13, 14. And here's a question. What day do you guys think he is going to run out of candy? Let's go to day 25. So we get 26.2144. We're timesing by 0.4, remember. So 10.48576. 4.194304. Getting close, aren't we? 1.6777216. 0.67108864. So what number do we have to hit for it to be all gone? 0, right? We hitting 0 yet? Getting pretty close, right? 0.1073741824. So if I keep doing this, I'm still getting decimals, right? And let me jump ahead to, let's see, to 25. At 25, I get this number. 0.1234 11258999907. Okay, is that 0? You might say yes, that's pretty close to 0, but it's not exactly 0, is it? Okay, and the thing is, if we keep going down, we're going to get some really small numbers, but we're never actually going to get it all the way completely gone. Okay? When would the candy be gone? Never. Because we're only taking a percentage. When you take a percentage and it's not equal to 100%, you're never going to completely get rid of something. You may get it so infinitesimally small that you can't see it, touch it, feel it, maybe not even see it with a microscope. But really, there's always going to be some little piece left there. So, for all intents and purposes, yeah, you could say day 25 for sure. Probably even like day 20. Because, how much candy really is that? So, you could say, that quick he's going to run out. But really, because we're only taking away 40%, we're left with 40%, we're always left with almost half of what we had previously. So it's never going to completely go away. So, now one more thing I wanted to show you guys. Let's take a look at all three of these questions graphically. I wanted to kind of just compare them real quick. So, if we look at those first two, problem number 1, that was our arithmetic one, 10 candies a day. And this one, the bottom one, was when he doubled it. Okay, so we can see off the bat, at the beginning, it seems like 10 candies a day is better, right? But then once we keep going, once we hit this point right here, okay, where they intersect, right? Remember systems, that intersection point? Then you can see how quickly that one shoots up, right? See that they just keep widening the gap quicker and quicker. That's how we end up here at 30 days at 300, and then 500 million. Okay, so that's kind of what it looks like if we're looking at the graphs. Now if we add in that last graph, okay, notice that it's this number 3 right here when he was giving away the candy. Notice that that one looks very similar to this one, doesn't it? The only difference is this one's going down and this one's going up. Okay, one other thing to notice, how we said that it's never going to get down to 0. See how this line just hits right close to that x-axis? It's just going to keep doing that. Okay. Alright, so there we go, guys.